Okay everyone, I spent quite a bit of time trying to figure out the most primitive and simple demonstration of Faraday's law. Here's what I came up with. I found this really old school galvanometer which displays current flow. I connected a copper wire between its terminals and will keep my eye on the needle to see if there's any movement which would indicate electrical current flowing through the wire. I'm going to take this large neodymium magnet and move it towards and away from this copper wire and see what happens. You can see that as I move the magnet towards and away from this copper wire, the galvanometer needle deflects. Make sure you notice that this deflection occurs only when there's relative velocity between the wire and the magnet. Even if the magnet is right next to the copper wire, if it's not moving, there's no deflection of the galvanometer needle. The significance of this can't be overstated. You're looking at the conversion of electromagnetic energy into actual work. Work as exemplified by this needle moving. I'm going to take this stack of button neodymium magnets and once again move the magnets relative to the wire. Instead of using a single strand of wire, I'm going to use an 800 turn coil of wires. I'm thinking if one wire is good, 800 turns of a wire is even better. I'm going to do this by dropping them through this plastic tube. You can see that as this stack moves into the coil, the LED flashes brightly. You can also see that when the magnets come to a rest, the flashing stops. Now I'm going to take this simple electric motor. You guys have seen these everywhere. They're in all kinds of everyday devices. If I open it up, I find a little spinning piece that's wound with yet more copper wire, a lot of it actually. Here you can see two permanent magnets glued to the outer casing of the motor. So once again, I have copper wire that's going to be moving with respect to a magnetic field. In this case, the copper wire is spinning and the magnetic field is stationary, but that doesn't matter. The only thing you need is relative velocity. Now watch what happens when I manually spin the coil of copper wire, which again is located next to fixed magnets. We normally feed electric motors electricity to get them to do work for us. In this case, we're basically flipping the script. I'm providing rotational kinetic energy to a motor, which then makes it a generator, as evidenced by the electricity produced that lights the LED. Check out this FET simulation. I have a permanent magnet sitting in the middle of a coil of wire connected to a light bulb. You can see a magnetic field definitely exists, but nothing's happening. Now watch what happens when I move the magnet and therefore cause a changing magnetic field, or a changing flux. What can be done to make this light bulb glow as brightly as possible? Well, I can increase the magnetic field strength by increasing the strength of this bar magnet. I can make additional loops of wire, and I can increase the relative velocity between the magnet and the coil. Just to reinforce the term relative velocity, I'm going to move the coil and leave the magnet stationary. When we studied thermodynamics, we looked at this flowchart from the Lawrence Livermore National Laboratory. It shows the basic energy sources on the left side and their application towards the right side, and on the far right side it shows how much energy is put to productive use and how much energy is rejected as waste heat. Now I want to draw your attention to the huge amount of energy that is spent on generating electricity. The vast majority of this electricity is generated via Faraday's law. It is not at all incorrect to once again look at this needle deflect when I bring a magnet towards and away from this single copper wire, and realize that this is the fundamental method used to generate the vast majority of the world's electricity. Box number 1. What does nature say about a conductor placed in a magnetic field? It says current only flows if there's relative velocity between that conductor and the magnetic field that it's exposed to. If the relative velocity between this conductor and this external magnetic field increases, the current flowing through that conductor also increases. As far as the direction of the current flow is concerned, you need to look at whether the external magnetic field's north or south pole is approaching or receding from the conductor. Remember, the north pole is defined as that area where magnetic field lines flow out of, and the south is the area where these magnetic fields flow into. A north pole and a south South pole are always together. We return to a conversation about flux, in this case, magnetic flux. You studied electric flux intensely in Chapter 23, which was Gauss's law. There's our definition of magnetic flux. Capital Greek letter theta subscript b for magnetic field equals the integral of the dot product between the magnetic field vector and the area normal to the surface through which the field lines pass. Do the dimensional analysis on the definition shown in box 3. Box 4 is showing us that from now on we're going to refer to a Tesla times meter squared as a Weber. This is the unit used for magnetic flux. Box number 5 is basically a copy and paste of what was introduced in Chapter 23, Gauss's law, but slightly modified for magnetic flux instead of electric flux. There are 3 ways to change magnetic flux. Change the strength of the magnetic field, change the amount of coil area exposed to the magnetic field, change the orientation between the magnetic field and the coil area, specifically the surface normal to that coil area. Box 6, Faraday's law, ties all of this together. The voltage you can induce or cause in a conducting loop is equal to the rate at which the magnetic flux through that loop changes with time. It's not enough to expose the loop to a magnetic field. You have to expose it to a changing magnetic field. It turns out when you do this, nature exacts a price. The voltage you create in this magnetic loop behaves in a way to actually oppose the change that you're exposing the coil to. Here is Faraday's law. The induced voltage, which is technically an EMF, electromotive force, which is why you see the script letter E, equals negative N d phi dt. The N refers to the number of loops. If one loop is good, then 5 loops is better. D phi dt refers to the time derivative of the magnetic flux that the coil is exposed to. That negative sign means the direction of the induced voltage opposes the current that created it. Let's look at checkpoint 1. This is taken directly from your textbook. Rank these 5 regions according to the magnitude of the induced EMF. Regions A and C are easy. They're flat lines, which means their slope is 0. So they're tied for the lowest magnitude. Regions B and E have a slope, but you can see the slope in region B is greater than that in region E. So the greatest induced EMF is found in region B. Region B has a positive slope. Region E has a negative slope, which is good to know, but your job here is just to rank by magnitudes. Box 7, insights, and there's a lot of them. First bullet, this is the magnitude angle version of the dot product. Second bullet, this integral is capturing the flux at a moment in time. Keep that in mind. Third bullet, once you have a snapshot of the flux at an instant, take the time derivative to figure out how it changes as a function of time. Remember, it's not enough to have flux. You have to have time-changing flux to produce an EMF. Fourth bullet, this is the common mistake, that dA is an integration variable. It's not referring to the derivative of an area. Fifth bullet is a product rule reminder. You might be engaged in a fair amount of integration when you work with Faraday's law. The last bullet is a good summary bullet. The goal here is to capture the time and space dependency of the magnetic field and the loop area, as well as their correlation. Keep that in mind as you solve these problems. More insights. Remember, the dot product is the product of parallels or anti-parallels. If your goal was to create the maximum flux possible, you would expose a really large loop to a really strong magnetic field, and you would orientate them so that the magnetic field is perpendicular to the plane of the loop, or parallel to the loop's surface area normal. It's not enough for flux to exist. It needs to exist and change as a function of time in order to create a voltage. Standard tactics here. You're splitting a given surface into teeny tiny differential sized elements. You figure out what the magnetic field line is doing at each element, and you integrate to sum them together to find the total flux. Here's another view showing the surface normal for each of the differential elements. You're taking the dot product to find the component of the magnetic field line that's parallel with the surface normal vector. Okay, let's spend a lot of time talking about Lenz's law. Lenz's law is basically the negative sign in Faraday's law. It says that when you induce an EMF, this EMF in turn creates an induced current, and this induced current flows in such a way that the magnetic field it creates opposes the initial change in the external magnetic field that started this whole thing to begin with. When you watch the following demonstration, keep in mind that the magnetic ball is falling through a tube made of aluminum. Aluminum is a conductor, but it's not magnetic.
So this is a super strong magnet ball that goes into this aluminum tube. Let's see what happens.
You can manage to put the ball into the side without it touching the...
Okay, another similar demonstration, just because it's interesting. In this case, the object is dropping through a copper tube. Like aluminum, copper is a good conductor of electricity, but it is not itself magnetic. Check it out.
This is Lenz's law, Kit. It demonstrates very nicely how magnets behave when they fall down metal tubes. We have a slug of metal here, and we're going to drop it down the tube, and there's a nice window in the tube so you can see all the way down, boom, down she goes. Turn it the other way up, and still it'll go down at good speed. It's called gravity. Well now, if we were to make a magic pass, drop it down again, something else might happen. Look at that, extraordinarily slowly. And the other way up. Oh my, oh my, oh my. Well, of course, there was a sleight of hand. This is highly magnetized, and this little buddy I showed at the beginning is not magnetized at all. The highly magnetized one is creating a little eddy current in the tube, which itself creates a little magnetic field that opposes the descending slug of metal, and it's trying to stop it going down. What a nice demonstration of it, too. Lenz's law, Kit.
Lenz's law says the induced current in a loop is in the direction that creates a magnetic field that tries to counteract the change in the magnetic flux through the area enclosed by that loop. Lenz's law is basically the negative sign in Faraday's law. The induced voltage creates an induced current, and this induced current flows in a way such that its associated magnetic field, which we refer to as the induced magnetic field, opposes the change in the initial magnetic field that created it. There is a pop can right-hand rule that you really need to master. Let's look at scenario A. I have a bar magnet and a conducting loop of wire. I bring this bar magnet with the north pole facing down towards the conducting loop. Since this loop is exposed to a changing flux, a voltage gets created. This voltage creates an induced current that you see represented with a purple arrow and a capital letter I, conventional current direction. This current flows counterclockwise through this conducting loop, which means an induced magnetic field gets created that flows upward through this conducting loop. This upward induced magnetic field is counteracting the downward and increasing magnetic field that caused it. This is nature's way of opposing the initial change to the magnetic field that started everything. Let's look at scenario B. The south pole of a bar magnet is being moved away from the conducting loop. The flux going through the loop is upwards, but it's decreasing. What will nature do to try to keep this upward flux maintained? The answer is nature will create an induced current, which in turn will create an induced magnetic field that is also oriented upward. The pop can right-hand rule tells you that the induced current must flow counterclockwise for this to happen. Scenario C. The north pole of a bar magnet is being moved away from this conducting loop. The north pole produces a downward magnetic flux. This downward flux is thus decreasing as the magnet moves away from the conducting loop. Nature doesn't like this, so the voltage that's created will induce a current flowing clockwise as shown. If you use the pop can right-hand rule, you see that this induced current must move clockwise around this loop. The pop can right-hand rule shows that a clockwise flowing current produces a downward-oriented magnetic field. This downward magnetic field is attempting to keep the initial downward flux unchanged. Scenario D. The south pole of this bar magnet is moving towards the conducting loop. The magnetic field produced by the south pole flows upward through the loop. If the south pole is approaching the conducting loop, this upward flux increases. Nature says, I don't like that. I'm going to create a downward magnetic field to oppose this increasing upward flux. Using your pop can right-hand rule, you can see that the induced current must flow clockwise to create a downward-oriented magnetic field. These scenarios are tricky. You should spend a lot of time poring over each of these situations. You should absolutely use your own pop can right-hand rule to confirm you really understand what's going on. The bottom of page 2 includes a general recipe to attack Faraday's law problems. Number 1, set up an integral that captures the flux at a moment in time. Number 2, think carefully about your variable of integration. Number 3, capture the orientation between the magnetic field and the surface normal vector. Number 4, look for any clues or evidence that addresses how this orientation may change as a function of time. Number 5, think carefully if the magnetic field B is constant or variable. If it's constant, bring it out of the integrand. Number 6, once you get all this set up, take the time derivative. If you have a uniform change with respect to time, you can use deltas instead of derivatives. Next section, induction and energy transfers, oftentimes referred to as motional EMF. Here's our setup. I have a resistor here on the left side. At the bottom, I have a conducting rail, and at the top, I have a conducting rail, and across both of these rails is a slidable conducting bar. The left side resistor, the bottom rail, the vertical sliding bar, and the top rail form a closed loop. This loop itself is exposed to a uniform magnetic field that's oriented downward into the page, as indicated by the X's. Some external agent applies a force on that slidable conducting bar and pulls it rightward at a constant velocity. This external agent might be you. Maybe you walk up, grab the bar, and slide it rightward. Maybe you attach a rope to this vertical sliding conducting bar and something pulls on the rope. Maybe a block that's falling under the force of gravity, or a horse, or something. In the drawing, you see a purple arrow labeled capital letter I, which is showing the induced current that gets created as a result of you pulling this bar rightward. Let's verify this with Lenz's law. If I pull that vertical bar to the right, the amount of downward-oriented magnetic flux is increasing. My loop area increases. The amount of downward flux also increases. Lenz's law says nature will respond by making the induced current flow in a way to counteract that changing magnetic field. In this case, the current needs to flow counterclockwise, which is why you see the conventional current arrow flowing from left to right through the bottom rail. That same current will flow vertically upward through the vertical sliding bar, leftward through the top rail, and down through this resistor. It's a simple series circuit, but it's enlarging as the bar slides to the right. Box 1, there's the general definition for magnetic flux. Box 2, theta refers to the angle between the magnetic field vector and the surface normal vector. Well, I know the surface normal vector is perpendicular to this loop, but is it perpendicular going into the page or perpendicular coming out of the page? The convention is to again use the pop can right-hand rule. Curl your fingers in the direction of the conventional current flow, which in this case is counterclockwise, and your thumb points up. So the surface normal vector for this loop is perpendicular to the surface area and is pointing upward. The area of this loop is L times X. L is a constant. X I need to leave as a variable because that will be changing as a function of time. Box 3 shows the updated expression for magnetic flux in this situation. Box 4 is a copy and paste of Faraday's law. So now spend a lot of time and carefully follow steps 5 through 16. Everything's straightforward. I just want to call out some highlights. In box 9, I'm using Ohm's law to get an expression for the induced current. Box 10 comes from chapter 28, where we did nothing other than figure out the force exerted on currents exposed to a magnetic field. Also for box 10, I need to use my flat hand right hand rule to figure out the direction of the magnetic force that's acting on that vertical bar. Keep your right hand flat. Point your fingers in the direction of the magnetic field, which in this case is directly down into the page. Your thumb points in the direction of the current, which in this case is upward. Again, we figured that out using Lenz's law. And your palm is pointing to the left. So I have a leftward oriented magnetic force that needs to be opposite and equal to the applied force, because if the velocity is constant, the acceleration is zero, which means no net forces. So box 11, constant velocity means zero acceleration. My rightward applied force is opposite and equal to the leftward magnetic force. Box 12, yes, I used my flat hand right hand rule to determine the magnetic force was oriented leftward, so the applied external force needs to be rightward. Box 14, I'm remembering the calculus definition for power. It's the rate of doing work. So in box 15, I'm figuring out the amount of work done by this externally applied force. It's just force times distance because the force itself is constant. Box 16 shows me the power produced by this externally applied force. Box 17 shows the power produced by this externally applied force in terms of the specific properties and dimensions for this particular situation. Box 18. I know that if current flows through that resistor, the power of the heat dissipation that results is given by I squared R. This is from chapter 27. Box 19. So I take a different approach and yet I get the same result for the power of the heat dissipation through that resistor, and notice it matches my result in box 17, which hopefully it does because the power invested by the externally applied force is directly translated into the power of the heat dissipated by that resistor. Inductors and inductance. You're looking at a picture of a solenoid, which we've studied in depth. This is also known as an inductor. Underneath this drawing is the schematic symbol for an inductor. Let's check out a few excerpts from the Engineering Mindset YouTube channel.
So what is an inductor? An inductor is a component in an electrical circuit which stores energy in its magnetic field. It can release this energy almost instantly, and we'll see how it does that later on in this video. Being able to store and quickly release energy is a very important feature, and that's why we're going to use these in all sorts of circuits. Now, in our previous video, we looked at how capacitors work. Do check that out if you haven't already, links down below. So how does an inductor work? I want you to first think about water flowing through some pipes. There is a pump which pushes this water, and the pump is equivalent to our battery in the circuit. The pipe will split into two branches, and the pipes are equivalent to our wires. One branch has a pipe with a reducer in it, and that reduction makes it a little harder for water to flow through it. So the reducer is equivalent to resistance in our electrical circuit. The other branch has a water wheel built into it. The water wheel can rotate, and the water flowing through it will cause it to rotate. The wheel is very heavy though, so it takes some time to get it up to speed, and the water has to keep pushing against this to get it to move. This water wheel is going to be equivalent to our inductor. When we first start the pump, the water is going to flow, and it wants to get back to the pump as this is a closed loop. This is just like when electrons leave the battery, they flow and try and get back to the other side of the battery. By the way, in these animations, I use electron flow, which is from negative to positive, but you might be used to seeing conventional flow, which is from positive to negative. Just be aware of the two and which one we're using. So as the water flows, it reaches the branches and has to now decide which path to take. The water pushes against the wheel, but the wheel is going to take some time to get moving, and so is adding a lot of resistance to the pipe, making it too difficult for the water to flow through this path. Therefore, the water will instead take the path of the reducer because it can flow straight through this and get back to the pump much easier. As the water keeps pushing, the wheel will begin to turn faster and faster until it reaches its maximum speed. Now, the wheel doesn't provide almost any resistance, so the water can flow through this path much easier than the path with the reducer in it. The water will pretty much stop flowing through the reducer, and it will all now flow through the water wheel. When we turn off the pump, no more water will enter the system, but the water wheel is going so fast it can't just stop, it has inertia. As it keeps rotating, it will now push the water and act like a pump. The water will flow around the loop back on itself until the resistance in the pipes and the reducer slows the water down enough that the wheel stops spinning. We can therefore turn the pump on and off, and the water wheel will keep the water moving for a short duration during these interruptions. We get a very similar scenario when we connect an inductor in parallel with a resistive load such as a lamp. This is the same circuit as we just saw, but I've just wired it more neatly. When we power the circuit, the electrons are going to first flow through the lamp and power it. Very little current will flow through the inductor because of its resistance at first is too large. The resistance will reduce and allow more current to flow. Eventually, the inductor provides nearly no resistance, and so the electrons will prefer to take this path back to the power source rather than through the lamp, so the lamp will turn off. When we disconnect the power supply, the inductor is going to continue pushing electrons around in a loop and through the lamp until the resistance dissipates the energy. So what's happening in the inductor for it to act like this? Well, when we pass electrical current through a wire, the wire will generate a magnetic field around it. We can actually see this magnetic field by placing compasses around the wire. When we pass a current through the wire, the compasses will move and align with the magnetic field. When we reverse the direction of the current, the magnetic field reverses, and so the compasses will also reverse direction to align with this. The more current we pass through the wire, the larger the magnetic field becomes. When we wrap the wire into a coil, each wire again produces a magnetic field, but now it will all merge together and form one large, more powerful magnetic field. We can see the magnetic field of a magnet just by sprinkling some iron filings over the magnet, which will reveal the magnetic flux lines. When the electricity supply is off, no magnetic field exists. But when we connect the power supply, current will begin to flow through the coil, so a magnetic field will begin to form and increase in size up to its maximum. The magnetic field is storing energy. When the power is cut, the magnetic field will begin to collapse, and so the magnetic field will be converted into electrical energy, and this pushes the electrons along. In reality, it's going to happen incredibly fast. I've just slowed these animations down to make it easier to see and understand. So why does it do this? Well, inductors don't like changing current. They want everything to remain the same. When the current increases, they try to stop it with an opposing force. When the current decreases, they try to stop it by pushing electrons out to try and keep it the way it was. So when the circuit goes from off to on, there will be a change in current. It has increased. The inductor is going to try to stop this, and so it creates an opposing force known as a back EMF, or an electromotive force. This back EMF opposes the force which created it. In this case, that's the current flowing through the inductor from the battery. Some current is still going to flow through though. And as it does, it generates a magnetic field which will gradually increase. As it increases, more and more current will flow through the inductor, and the back EMF will eventually fade away. The magnetic field will reach its maximum and the current stabilizes. The inductor no longer resists the flow of current and acts like a normal piece of wire. This creates a very easy path for the electrons to flow back to the battery, much easier than flowing through the lamp. So the electrons will flow through the inductor and the lamp will no longer shine. When we cut the power, the inductor realizes that there has been a reduction in current. It doesn't like this and tries to keep it constant, so it's going to push electrons out and try to stabilize it. This will power the light up. Remember, the magnetic field has stored energy from the electrons flowing through it, and it will convert this back into electrical energy to try and stabilize the current flow. But the magnetic field will only exist when the current passes through the wire, and so as the current decreases from the resistance of the circuit, the magnetic field collapses until it no longer provides any power. If we connected a resistor and an inductor in separate circuits to an oscilloscope, then we can visually see the effects. When no current flows, the line is constant and flat at zero. But when we pass current through the resistor, we get an instant vertical plot straight up, and then its flat line continues at a certain value. But when we connect an inductor and pass current through it, it will not instantly rise up. It will gradually increase and form a curved profile, eventually continuing at a flat rate. When we stop the current flowing through the resistor, it again instantly drops and we get this sudden vertical line back down to zero. But when we stop the current through the inductor, the current continues and we get another curved profile down to zero. This shows us how the inductor resists the initial increase and also tries to prevent the decrease. What do inductors look like? Inductors in circuit boards will look something like this. Basically just some copper wire wrapped around a cylinder or a ring. We do get some other designs which have some casing over. This casing is usually to shield the magnetic field and prevent this from interfering with other components. We will see inductors represented on engineering drawings with symbols like these. Something to remember is that everything with a coiled wire will act as an inductor. That includes motors, transformers and relays. So what do we use inductors for? We use them in boost converters to increase the DC output voltage while decreasing the current. We can use them to choke an AC supply and only allow DC to pass. We can use them to filter and separate different frequencies. And obviously we also use them for transformers, motors and relays. How do we measure inductance? We measure the inductance of an inductor in the unit of Henry with a capital H. The larger the number, the higher the inductance. The higher the inductance, the more energy we can store and provide. It will also take longer for the magnetic field to build and the back EMF will take longer to overcome.
There's a lot of similarities between inductors and capacitors. Inductors store energy in a magnetic field and resist sudden changes in current. Capacitors store energy in an electric field and resist sudden changes in voltage. This is our third type of passive electronic component to go along with resistors and capacitors. Inductance is the property of a conductor by which a change in current going through it induces a voltage in both the conductor itself and in any nearby conductors by mutual inductance. Here's our definition of inductance. If we do the dimensional analysis, we get a new unit, the Henry, which is equivalent to a Tesla square meter per area. Let's study the inductance of a solenoid in detail. This first bullet, the magnetic field lines from each turn of the solenoid pass through all turns, so an induced voltage in each coil opposes changes in the current, should be apparent after all of our conversation about Lenz's law. Each turn of a wire in a solenoid feels the effect of the magnetic field created by every other turn in that same solenoid. Box 1, we start with the general definition of magnetic flux. Box 2, we like solenoids because the magnetic field inside them is really uniform. By now, hopefully you can see that the angle between the magnetic field vector and the surface normal area vector of a solenoid is 0 degrees. Don't gloss over that though. Let's talk if it's not clear. Box 3, we actually derived the magnetic field for a solenoid in detail. The bottom of box 3 shows our updated expression for solenoid flux. And there it is in box 4. We have our expression for solenoid inductance. Like capacitance, inductance only depends on the solenoid's geometry, in this case the cross-sectional area and the length of the solenoid itself. Next section, self-induction. Have you ever noticed in your house when you turn on a large motor, for example, an air conditioner or a vacuum cleaner, and you notice the lights briefly dim at that moment? I have. That's an example of what we're talking about right now. Look at this circuit. It's a resistor, battery, and switch. I close the switch and current begins to flow. We know from chapter 29, a current creates its own magnetic field that also grows along with the current. A growing magnetic field constitutes a changing flux, and we all know that a changing flux creates a voltage. This induced voltage, in turn, induces its own current. This induced current induces its own magnetic field. This magnetic field is created in such a way to oppose the original changing flux that produced it. The voltage that induced this opposing magnetic field is known as back EMF, EMF electromotive force. This effect is known as self-induction. The resulting induced voltage opposes that of the battery. This means that when you close the switch, rather than instantaneously go from 0 to full value, the current gradually goes from 0 to its maximum value. Okay, let's remember the definition for inductance. Inductance L is defined as N times the flux divided by the current flowing through the inductor. We remember Faraday's law. So here you have the expression for the voltage drop across an inductor. That minus sign is, once again, Lenz's law. It's created in such a way to oppose the initial changing current. Okay, last section, RL circuits, resistor inductor circuits. This is going to look a lot like charging and discharging RC or resistor capacitor circuits. As it says here, RL circuits sometimes are used to block high frequencies while allowing direct current flow. Here's our RL circuit. We throw this switch from position B to position A. Current flows from the battery through the resistor and into the inductor. Just like that water turbine you saw in the engineering mindset video, the inductor has some inertia, so to speak. At first, it's very difficult for that current to move through that inductor. The inductor, for the first few moments at least, is impeding the battery. We apply Kirchhoff's loop rule. We get a voltage rise across the battery, but a voltage drop across the resistor and another voltage drop across that inductor, because that's what inductors do. They impede the battery. A through H, I think, are pretty straightforward. Everything started with the loop rule. I through Q are also pretty straightforward. Let me draw special attention to M, another time constant. Tau subscript L is defined as L over R. Look at this graph in box N. When you throw the switch, it does take a while for the current to reach its full value. It doesn't happen instantaneously. This shark fin shape is something you saw before with RC circuits. The current reaches 63.2% of its maximum value at T equals tau seconds after the switch is closed. The graph in box O shows the change in current as a function of time. When the switch is first closed, initially there's no impedance. In box P, let's look at the voltage characteristic for the resistor in that circuit. Ohm's law says V equals IR. We have an expression for current, so we once again see this logarithmic growth characteristic for the resistor in this RL circuit. Box Q, let's look at the voltage characteristic for the inductor. At the very beginning, or the transient response of this inductor, looks like it's behaving like a literal gap in the circuit, just like a fully charged capacitor looked like a gap in a fully charged RC circuit. Over time, though, the impedance of this inductor fades away and it now looks like a wire. Just like the transient response of a capacitor in a charging RC circuit looks like a wire with no resistance. Let's talk about a discharging RL circuit. I throw switch 2 from position A to position B. Now the inductor will discharge. Here's my loop rule in box A. The only thing missing is the battery because, again, I switched it out. And there you see the current characteristic for a discharging capacitor. You get an exponential decay curve. If there was no inductor in this circuit and you throw the switch, the current would instantly fall from its peak value to 0. It's the inductor properties that explain the gradual exponential decay. Last section, energy in a magnetic field. We go back to the charging RL circuit and once again apply Kirchhoff's loop rule. Follow what's happening in steps B, C, D, and E is the expression for the magnetic potential energy contained in an inductor. Notice how similar it looks for the expression describing the electrostatic potential energy between the plates of a capacitor.